Hello. Okay, thank you, even though I didn't understand the intro. So I'm going to be talking about OpenCV and its developments, and also spatial AI and some of its implications. So as an outline of my talk, I'm just giving an overview, since the new generation is coming, like what my background is, the OpenCV history, the new OpenCV 5 that's coming, spatial AI that we're developing, and implications for general intelligence. Hopefully I'll keep this timing going. So my background, I'll just start with UC Berkeley. I traveled the world, and I came back and started working contract software, and ended up then going, as I intended, always a little bit later than I intended, going to a grad school where I studied neural networks very early, before they were big. And one of the guys I used this code and became friends with was Jan LeCun. And so he did well later. and so, I went to some jobs and eventually worked on the autonomous car at Stanford, where I was consulting faculty for 7 years. But mostly I started doing startups, and so I've done a lot of startups that most of them have ended decently. and now I've kind of moved into investor advisor, and I work a little in some startups, and I'm trying to build up the support of the financial support of the open source foundation and move it into the AI future. So these are my focuses now. Okay, I don't know how many of you are users of OpenCV somewhere. Yeah. We did a survey at CVPR and found that 80% of startups are using it in some way. It also has got 400 million downloads this year, so it's extremely active. And here is kind of a world by regions of activity. Color-coded, brighter is by darker green is more activity. Of course, China is the greatest because it also has the greatest population. So, but generally, this chart is kind of the area of a look at where technical development in AI, computer vision, all the stuff is. If you threshold it some. So we're moving towards an Apache 2 license fully, and with all kinds of languages, all kinds of hardware support. So I'll get into that. So OpenCV at a glance. It started out with classical computer vision, and we actually had the first DeepNet learning library, but it was just too early. So we translated Jan's stuff, but it was just too early. There wasn't enough data. There wasn't enough compute. No one used it, and so we dropped it. Too bad. I should have stuck with it. But we have basics in image processing, image transforms. These are actively used. Fitting, optical flow is still actively used. Segmentation has gone more deep. Calibration is still a big category, and we're improving it. I'll talk about that a little. SLAM, 3D is growing, computational photography, but the main area, like I circled here, is in DeepNet. So the DNN runs inference for DeepNets on all kinds of hardware. A lot of that development is happening in China. We have a team in Shenzhen that we work actively with. And at the bottom, you can see some of the models. We're trying to fully support ONNX and Intel, on CPUs, OpenVINO, and on and on. ARM, we've recently done a whole optimization on. Qualcomm, we're doing optimization, and we're working with many of the chips in China. So a brief kind of developmental history. I started this when I joined Intel. partly because I was chartered. We were doing word processing and spreadsheets, and they thought, well, there's already enough compute. Where are we going to create a demand for more cycles? And I go, obviously, in AI, computer vision. And so I started developing the library to support that, also because I wanted to use my work when I left Intel. But that really worked. It helped develop the field. Before then, you could never repeat what someone did because it was their own code and everything. So this gave at least a code base that was common, that you could reproduce, say, CVPR, whatever, publications or scientific work. In the next stage, I went to Willow Garage. We got funding, and we modernized to C++, brought it into mobile and Git and all the more modern tools. And in 2016, we started, fully developing this deep DNN module for deep learning, for inference. And now we're going to do 5.x, which is focusing a lot on embedded edge AI and performance optimization. So the developers and contributors, of course, center around Silicon Valley as a start in the US. Russia, there's always been a Russian team. It goes back to my Intel history and getting to know these people, and they're still actively developing both in Russia. Some of them now work for Huawei. And then we have a whole team in Cyprus who are doing AI contracting that still contribute. And then I mentioned in China, especially around Shenzhen, so they're doing a lot of the optimization work. They contributed to face tracking and identification module. And of course, we have probably the dominant group is the worldwide developers at any given time. There's kind of like 100 active contributors they come and go, but probably the bulk of stuff comes from them. So, OpenCV, I said we're trying to move towards faster and faster execution of computer vision. And the ways we do this is we have this generalized parallel 4 that gets translated into different architectures. We also have universal intrinsics, which are, you can think of them as DSP optimizations, and that roll out into different architectures that support this. So that's a universal intrinsic that then translate into the specific kind of DSP style operations on various processors. And of course, GPU with CUDA and OpenCL, and that devolves into the GPU architectures. So those are like how we're trying to keep things accelerated across the board. We're working with various chip people to do specific optimizations on their architectures. And this shows up in our model zoo. So there's an OpenCV model zoo, and you can see some of the active support already. Several of these are in China and MPU, but there's also ARM and of course CUDA on the NVIDIA architectures, and on CPUs, OpenVINO and whatever. So there's hardware types and the actual chips that the DNN library allows, the module allows optimization on. This is an example, and this is the face detector, which was developed in Shenzhen University with Shiki Yi and his group. But I'm just using this to show the other thing I'm trying for, and I always did for OpenCV. There's very complex libraries and hierarchies. I want to just forget that. Just do what you want. It's few lines. It's kind of like the old Python. I want as few lines of code. That's the ideal to get what you want. And so here you can see we're instantiating a face detector. And then down here, like in red, I got you give it the type of hardware. So this is a TIMVX hardware. And then and if there's the actual chip, and you can just give it suggestions too. So it'll run on anything. But if you know what you're running on, this will give the highest performance. And then you just run it, and it gives you the face detections, which are being displayed here. We're also doing a lot in depth perception, and it's the same kind of thing. This is with Orbeck, and which makes a high-quality stereo. So you just instantiate the detector, ask it for the RGB image and also the depth image, and this little code here is just turning it into something that's human understandable, readable below. So there's a depth image, and then it's display in depth, the RGB above, and then the display of depth map below. So OpenCV 5 is where we're going. This should be coming out end of this year. We've been saying that for a long time, but it is getting much closer. I go, like, why OpenCV, or what's coming in it? And the first of all is like a complete revamp, so to OpenCV, I mean C++ 17 minimum standard and above. Optimized performance, I talked about some of that, over a large variety of hardware. We're doing a complete switch to Apache 2 license. This is just a little bit better for legal reasons. Licensing. We've done a lot to make error reporting, logging, and debugging easier. We've improved camera calibration quite a bit, these core modules that are highly used. Documentation's getting better, and we're hoping to come out with some kind of chat model over this as a general interface. The DNN module, the DeepNet, I talked a bunch about, so a lot of work has gone into that, revamping it and making it faster. I'll talk about spatial AI, but we also, we have a 3D module is getting a lot of work. We're improving fiducial patterns. We have the Tencent code, the actual code Tencent uses to do barcode detection. So we're improving that, and better detection, more robust, and we also have, OpenCV.ai is a professional. If you need development help, there's a lot of Russians in Cyprus who do contract programming over PyTorch, computer vision, AI, and whatever. And then CVAT AI is a data labeling service that's widely used. We also have OpenCV University that has a whole bunch of courses that are mostly on AI, but also a whole section on OpenCV. So here's some of a quick review. I'm going to check my timing here. Of the model zoos for DeepNet. So there's these open model zoo, and I'm showing some on your right. So there's, I don't know if you can see it from here, there's face detection, emotion recognition. There is face recognition, but tracking modules, segmentation modules, hands, the body pose, there's the fiducials being shown, and license plate or text recognition out in the wild. On the left here are professional models that OpenCV.ai has done that are very high quality, very stable for doing specific things. Here it's pet recognition and background segmentation and separation. Again, maybe for driving, pedestrian protection, and they've done a lot of work in medical and all kinds of stuff. This is text recognition out in the wild, and the sign recognition. So these are just some examples. This is okay, it is running. This is colorization, so black and white on the left is being turned into color on the right by deep nets. And in whatever in video, there's all kinds of edge detection, edges like humans would draw, or dominant edges in the image, which is useful for many apps. This is the segmentation. It shows a horse a mask being created and being used, and then in a video, this woman is being taken into a different background And so these things are in the DNN module. I already showed some of the face detections. Here you could see it's detecting the face and the emotion. This is recognition, so that Shiki is right in the middle. That's his lab, but here's one of his students being detected. I took some of the foils from his groups to keep it in China. These are deep tracking modules that are very robust and useful for drones and security and many other things. So tracking has become much more robust as a person being tracked in different contexts. These are stabilization. So we have top left, the moving image, the optical flow vectors for tracking on the right. Bottom left is the stabilized image of the above, and then this is centered and locked. So you can see that with a lot of stuff going on, you can keep it locked on one area of the image. So I'll just let this run again with the explanation a little bit. So you can stay focused, stay tracking. This is work that was done at one of the startup companies, but a lot of these techniques have moved into other industries in OpenCV. In particular, a lot of basically Tesla's whole calibration was extracted from Array and is what they do in their cars to calibrate their sensors now. It used to not work at all because they weren't doing much of anything, but now it's using these kinds of techniques. We did this for one of the Super Bowls, and so this is tracking and putting stable graphics on the background, and for movie work, you can see this car was overlaid in real time with a car. Here it was on stage, and it's being overlaid. This is a stable tracking that people can move in front of it and it's not bothering any of the tracking. Again, you can see this kind of thing. These are deep points. This kind of work is actually going to be landing on the moon in February. This algorithm basically that gives a barcode to each pixel in the image, and it makes things very stable and robust to occlusion and lighting and other stuff. So these are some techniques that are rolling out. I told you, because fiducials end up being, of course, in China you're using them for everything, but they're useful for a lot of things, including tagging scenes, helping put together scans, and so we've improved the detection and reliability of these things a lot. This is text in the wild and license code on the phone and just handwriting. So these are DNN modules that, one line of code and you've got them. This is body tracking. This is an example taken from other work, but this is the algorithm that's instantiated, and it's quite reliable for speed and whatever. And we hope to sort of track the state-of-the-art models and just keep them in there. Okay, this is again work in China, but it's using the hand detector to reflect it into a robotic model. And this is actually Shiki's kid, so I put him in for tracking, having a robot track him. And again, robot control by hand signaling or body signaling in a hallway. And so just let this run a little bit and then talk about spatial AI, which is a new initiative. So this is just the robots responding to pose recognition. I don't know how long I should let this go on. That's enough. So spatial AI, which is, embodied AI, is a kind of a Venn diagram overlap with spatial AI. In bringing the OpenCV forward, it's starting to make modules, and this is going to be one of the, not a foundation model, but a foundational module that I want to bring in easy, at least indoor scans of spaces, and then doing spatially aware AI on that. And we're looking at incorporating FutureWay and many other technologies, like not kind of riding on the state of the art of capture, and then I want you to be able to put up sensors and robots and have them be able to localize and manage many cameras, many systems that are fixed or moving in this environment. So these are just some of the capabilities of, like, what is spatial AI. Like, one aspect could be monocamera depth, so you can infer depth from a single image. We can do this easily. People can play basketball with one eye covered. They can learn. 3D capture, like, I want to get a reliable 3D capture of space. I guess in vehicles there's a lot of people doing this, but it's kind of frustrating indoors. There's no thing you can just open up out of the box and get a 3D scan that's reliable. It's kind of, after years, this SLAM technology. But so, we're trying to bring in state-of-the-art and make that easy. And then use the 3D model to localize AI detection, segmentation, ID categorization in this space. You can think of, in a house, I want you to be able to scan a space and put up security cameras and just have them identify, so you don't have to localize the cameras carefully. They'll know where they are. They can move and relocalize themselves, and then do whatever detections for the house. You can think of detections as, what do you want? People, detection, ID, location. You want the same thing for pets. You probably want a background maintenance and, like, things have changed model, and there's not a lot else. and I want to make that, like, we might just offer that as an open source AI where, no one is spying in your house, and you can have it locally on site and keep your data secure as a module of the system. But the spatial AI is not just that. It's obviously the most advanced, where it's these visual transformer backbones, and that are basically getting the what, where, and why in a scene. So the why is the physics, the causality, and they're like, Fei Li has just launched a large company to go after this. And we're not really going after this because I want something keeping with the philosophy of OpenCV. The spatial AI, the model is just going to be very simple, a few lines of Python, and you set up your system and it's running. And as these things advance, we'll incorporate them. But robotics also falls in this. They're kind of a complement, having knowledge, 3D knowledge of a scene, and the robot having 3D knowledge of the scene, and the two together can work together for enhanced safety and operation. And so that's going to be the foundation layer of embodied AI. And these are just some examples of the technology. This is work in the Apple AI, the Vladlen Colton's lab of, like, it's probably the state-of-the-art monocamera depth, and you can see it's done quite well and gets the edges quite well. And so, we might incorporate various states-of-the-arts in this, but there's also, probably state-of-the-art indoor capture, or at least object capture, is master or mass 3R. And it can do point alignment over extremely wide viewpoints by using these deep key points and confidence models. And it does object detection We've done some room detections. It's not totally, so people are already extending this to a master structure from motion, SVM. And so we'll be looking at that. But so this will maybe one of the bases in the spatial AI model. This is getting towards deep SLAM, and this is just showing other people's work in key point tracking, getting depth maps from the cameras, it could be mono cameras, but aligning them in poses and then refining that in a bundle adjustment to get a coherent 3D background. And you know, the example that I'm talking about that we hope to deliver is just this 3D model capture. So you capture the room, maybe capture your house with an iPhone or a camera. You get a 3D model that's able to localize other cameras, and then a simple, you know, we're looking at Dora and Xeno as possibly simple bit transports of devices. So future way, I want something that's very simple for doing bit transports and even just simple priority queues of sampling cameras and doing either localization and or AI on those views. And that's just the basis of a security system, and keep it simple for now. And you know, with depth maps, you can get accurate 3D poses with the AI, but you know, just keep that very simple. And so I've talked about this more advanced stuff, the vision transformer models that people are doing, robot control over these models. And so, you know, this is the stuff in spatial AI, and we'll probably be adding this in as it matures in a couple of years. But, you know, so robotics and whatever intercept with the spatial AI, as I discussed. And we're starting a conference in this, and so we'll be at this is with the Society of Information Display. It already is a 12,000 person conference, and we're running their vision for it because displays have been associated more and more with cameras. And so spatial AI makes sense there, and so we're starting this off, but we'll probably separate this out into a conference that focuses on this area. You know, many conferences have grown out of OpenCV, so we're probably taking that back in and doing it in this area. And so I just wanted to talk in the end. How much do I have? 10 minutes, okay. So I can talk slow. I'm just doing this on the implications for AGI, AI. I've been working in AI for, well, I'm friends with Jan LeCun. I know Hinton and Poggio and Bengio, and I've been thinking about this for a long time, and actually did a PhD that included biological intelligence. So I have a lot of background in what's being done and what's next and what's coming, and so. One of the things humans do is our learning is curriculum learning. I teach you addition, subtraction, then we generalize to multiplication and division, and then on up to linear algebra, and on up to quantum physics, you know, in steps. And that's how you learn. And it's built step by step. AI learning is, and our learning is always on. AI learning is completely different. It's based on IID, so independent, identically distributed samples. You get all the facts in the world, and then you just draw on them randomly because you're learning in a gradient, and you don't want to bias it into a direction. So if you did curriculum learning with AI, not only would the learning would be badly, it wouldn't learn anything at all. You would just get a slur of weights that don't learn anything. So that's why they turn off the learning, and the models you use, llama or whatever, they're what I call zombie brain tissues. You know, the paradigm is zombies eat brains. Well, that's essentially an AI model today is a chunk of associative brain tissue that you take out a refrigerator, put in your prompts, which are the electrodes, turn it on, you get an answer, and then you put the brain back. And it doesn't learn online, whereas humans are learning online all the time. And so that's a fundamental difference in learning, which is really one of the big bottlenecks to this AGI, because although you'll see if you use OpenAI models, they're getting better and better at reasoning. It's pretty amazing, but they're just those are just associating forms of reasoning and then going through the steps as they do a lot of reinforcement training to keep it in the guidelines. But it's incapable of doing true reasoning, because true reasoning is a curriculum learning. You go, aha, this, if this, then that. It's a curriculum, and I just said it can't learn in curriculum. In fact, it can't really learn at all. When current AI keeps models, all they do is they build a larger and larger kind of prompt context. And so, this is like one of the fundamental problems in AI, and why is it related to spatial intelligence? Because I think if I were now a new PhD, I would be looking at learning SLAM, simultaneous localization and mapping. That's put a robot in a room and it starts to learn and use the map that it's learned. But of course, that means it has to keep learning. And so the solutions of that are kind of the stub of the solutions for doing this always learning, curriculum learning type of thing. And so that's one of the clues I would look at. In human intelligence, one of the insights is we do a lot of simulation and matching to simulation. Like I could do a whole lecture on how our perception system is just a model. And we match to the perception. If I were to accidentally step off the stage, I would get this shock because I thought it was, my modeling was there was floor there, but it's not there. And I would do an instant learning because of the shock of the disconfirmation. And so obviously that's part of our system of doing continuous learning, is to not learn when our expectations are fulfilled. And so if I'm getting what I'm expecting, I'm not really learning. I can agree. In fact, that's mostly how we communicate. The only reason I can communicate with you is because I'm expressing tokens, which are actually parts of the brain state that you have. And if I can transfer my brain state, instantiate it in you, then you have an understanding. If I can't, then we don't learn. And of course, humans can then, get a disconfirmation and then learn, oh, I don't understand. If someone's not understanding like a math lecture, it's because they don't have some background and they're not able to instantiate the states. And this causes a learning signal, which they may or may not use to properly learn. But that's how that works. So, I would say this learning to operate ongoing in space is to me, is the simplest first step in being able to complete this learning. It's clear that it's not only that we only learn on disconfirmed expectations, but there's something fundamental in sleep. Sleep is so dangerous evolutionarily that we shouldn't do it. And yet we do. So it must be there's some kind of reorganization that's mathematically fundamental to learning, that you cannot get away from that. And I guess this is the noise generated from learning has to be resorted. And that's not well understood. Anyhow, these are just some ending comments on a pointer to AGI. And one of the key things is this catastrophic forgetting. If we can overcome that, we can move on to systems that are always learning, that go on to the AGI. And just to reiterate, that SLAM is like a nice sub-model of that. If you can wander around a space that's changing and keep learning it, then you could maybe start generalizing that to a space of tokens that you're wandering around. Anyhow, that's all I have.